Hi, good evening, everybody. Thanks for coming, really appreciate. It's my pleasure to welcome everybody here in the room and on the web as well, because we are doing this presentation also simultaneously on the web. This is the fifth of our 2023 C-Secret series. And my name is Rani Avisar, and I'm the Dean of the school. And again, this evening we are going to hear a presentation from Dr. Majumdar that has been essential, I would say, and a leader in establishing the Resilience Academy at the University of Miami. And you'll know in a few minutes what this is all about. We just would like to take a moment to thank the sponsor of our C-Secret series. And I will start with the Bank of America, which is our presenting sponsor, the Shepard Broad Foundation, Bill Galway. We have also Cheryl Gold, that is with us in the room, KB Life Enhancement Forum, Key Biscayne Community Foundation, John McCann Family Foundation, Gail Nansen in honor of Russell Nansen, Nicole and Myron Wang, and Southern Glazer Wine and Spirit. It is a tradition that we have now in this series, before the main speaker, to bring back an alumni that has been successful outside of the school, that graduated from the school and has done on his own or her own great activities as well. And so this evening, it is my true pleasure to welcome back to Rosenstiel Lisa Bucci, who in fact got her Ph.D. With Dr. Majumdar. And she was also co-advised by Dr. Atlas, who was the director of the NOAA AOML, a lot of acronyms. NOAA, I think that I don't need to spell that. AOML is the institution across the causeway that focuses also on meteorological research. And she's a hurricane specialist at the National Hurricane Center. And she previously worked at the NOAA AOML Hurricane Research Division. And as I mentioned, graduated from with Dr. Majumdar. Lisa?
Thank you so much for that introduction. So I spent 5.5 wonderful years here at the Rosenstiel School, where I had the unique opportunity to both continue to work as a scientist affiliated with the laboratory across the street, like the dean said, and do my studies here. And part of that unique opportunity meant that I got to do some of my Ph.D. studies flying into hurricanes. So the question that I get asked the most is, what's it like to fly into a hurricane? So I brought along a video to show you, to demonstrate it. So it's loud, right? This is what it's like to fly on the NOAA P3s. The video starts off in the eye wall. This is the most turbulent part of the storm where the strongest winds occur. And you can see that the rain is just streaking across the window. But as the video goes on, you'll see the sun start to come out, the rain starts to lighten, and all of a sudden you're in the eye of a hurricane. This is Hurricane Lane off the coast of Hawaii, which was a Category 5 hurricane. And in a moment, I'm going to point the camera up, and you're going to see the blue skies. And after that, I'll point the camera down, and you'll see the waves just crashing beneath me. And all around, you'll see this eye wall, where this stadium of clouds is just rotating around me. And you're thinking, are you just there to take videos? No. I'm there for science. I was doing research at this moment. I was actually operating a new instrument on the moon called a Doppler wind lidar. It collects winds in areas of lower precipitation and no clouds. So, but I had to just take a moment to take a video of this amazing imagery. So it was exciting. So I was actually trying to see if this new instrument would work. I had demonstrated that it worked in tropical storms and lower end hurricanes, but I'd never tried it in something major like a Category 5 hurricane. And I thought for sure this isn't going to work. I'm not going to get any data. There's too much rain. There's too many clouds. But actually, what I found was I did get it to work. So compared to what I would have normally gotten without this instrument, you see the image on the right, and that's where you can see a lot of dark blue. So you're getting some data as you're flying in and out of a hurricane, not a lot. But when you added the LiDAR data, what I found was that it was filling in some of these gaps. And I was getting a lot more information, as you can see from some of the warmer colors that are going into green and red beneath the aircraft. So this was really cool. It was really exciting to be able to not only get to see that, but to see my instrument work in an environment I didn't expect it to work. So I got to learn a lot about how to use the aircraft and how to think about how I want to fill in gaps with the instruments and the aircraft, moving on outside of my career here at the Rosenstiel School. So now I work at the National Hurricane Center. I actually that's me forecasting Hurricane Lisa this past year, which was really exciting. So sometimes if you ever check out some of the products, maybe you'll see my name at the bottom. I'm the second woman to ever hold this position, which is pretty exciting, and I'm loving it. And I got to bring over, and part of the reason why I got this job was because I'm bringing over this information that I learned about how to use the aircraft and when to use the aircraft. And so I got to help plan a mission into what wasn't Ian yet. It was just a tropical wave, but it ended up becoming the major hurricane that hit the southwest Florida peninsula. And I got to give some information about how we should plan to have aircraft into systems before they even form. We want to know when and where these are forming, right? We want to extend that forecast so we can get the forecast to you in the future. And I got to plan this mission into Ian, which you can see in the image on the left, so that we could help get this better forecast to you sooner. And those are just a couple of the lessons that I've learned while I was at the Rosenstiel School and have brought on into my career thus far. So thanks for having me, and we look forward to hearing Dr. Majumdar's speech.
Thanks, Lisa. As a pilot, I'm jealous, okay, that I cannot be with you over there. It is now my distinguished pleasure of introducing Dr. Sharan Majumdar. Sharan received his degrees, bachelor and Ph.D. At Cambridge. And in 1993, while he was on an internship in Australia, he realized that mathematics is great, but meteorology is even more important and more interesting. And so he decided to join the US in 1997, first at Penn State, which has a great department of meteorology. And he was there as a postdoc for a few years and was recruited at the University of Miami in 2002. And he went through all the grades of professorship. He is now with us, a full professor since a few years ago. Sharan served as an associate dean of graduate programs for a period of 3 years, 2016 to 2019. He teaches the classes in meteorology at the undergrad, graduate level, and with all kinds of aspects of the meteorological field, including diagnostic and forecasting. He's very active participant in the American Meteorological Society and the World Meteorological Organization. As I've mentioned before, he was one of the two co-director of the Resilience Academy, which is a new concept that was introduced at the university a couple of years ago. Sharan, all yours. Thanks.
Okay, thank you all very much for coming. It's really great to see everyone, especially with this rather terrible weather we've been having, which is probably quite appropriate for a talk like this, since it's about various elements of resilience and bad weather. So yeah, thanks for making committing your time in all this Miami traffic. And big thanks to the organizers and sponsors and Dean Avisar for having me here. So it's very interesting having Dean Avisar and Lisa sort of speak before me, because they both represent two of my favorite elements of being at the University of Miami. So with Lisa, of course, as with all my other grad students who are all here as well, that it's just one of the most rewarding elements of being a professor is really having the fantastic grad students who do terrific research. And also teaching a lot of very interesting courses, although I think they find them interesting. They're definitely challenging, hopefully. And then on the other side, working with Dean Avisar has been a lot of fun as his associate dean for a few years. And then also with the Climate Resilience Academy, that's also sort of my administrative hat as well that I've been wearing for a while. And so I'll be discussing that. But really to build continuity from what Lisa was discussing, we'll first talk about hurricanes and some of the challenges there related to resilience to hurricanes, with, of course, Hurricane Ian as an example, a very recent one. And then some of the forecasting challenges that forecasters such as Lisa are facing at the National Hurricane Center, and the types of research that we're all trying to do here at the University of Miami and with many collaborators to try and address many of these different forecasting challenges. And then after that, I'll discuss a little bit about this exciting new initiative called the Climate Resilience Academy that we're forming across the university. So there's a lot to discuss. I could really discuss this forever, but we'll try and keep the time here. Here's what a hurricane looks like. The left-hand picture here is of Hurricane Ian, so it's just as Lisa showed, although she had lightning in hers. And so we see on the satellite that it's just this awe-inspiring the moving system with this eye inside it. But beneath that, as we all know, lies a lot of potential for damage, unfortunately. On the right-hand side, we see here, this is the anatomy of a hurricane if one opened one up. It's not really to scale. It's like about 12 miles high or so, and it's a few hundred miles wide. We have the eye, and the eye wall, as Lisa mentioned, is the most violent part of the hurricane, where the strongest winds are. And then we have outer rain bands here as well. And then the wind field in the hurricane does extend out beyond the eye, and so it's important to be preparing and evacuating from a hurricane before the tropical storm force winds start to come. Those can extend, say, sort of even about 100 miles out or thereabouts. So a hurricane is sort of known as sort of one of nature's heat engines in a way, that there's a circulation, that we have air that sort of spirals inwards, in towards the eye and the eye wall and over the ocean. And as it's spiraling in, that it's exchanging energy with the ocean. And so the ocean serves as an energy source. And with that there's water vapor that then condenses into water and then creates what's called a warm core in the middle of the hurricane. And then that really helps the hurricane strengthen. And at the top of the hurricane, there's the outflow. So that kind of serves as the exhaust of this engine here. Moving on to Hurricane Ian, this is a report that this name may look familiar right here. It's a 72-page report that Dr. Bucci led, which is part of a requirement by the National Hurricane Center that for every single storm that's there, even the most sloppy tropical depressions that nobody ever cares about, that there has to be a report that's written about at the end of the year. And of course, with storms like Ian, there's a lot of work that goes into it. And so Lisa and colleagues prepared this 72-page report that came out last week. And it also upgraded after looking at some retrospective data that Hurricane Ian was a Category 5. As we see here, what this is the storm surge analysis that was done after the event. And these colors represent storm surges between 10 and 15 feet, unfortunately. And as we know, there was a lot of loss of life from Hurricane Ian, much of it, but not all of it, from the storm surge. And then on the right-hand panel here, we see this time sequence from the camera that held remarkably sort of steady, tied to perhaps a very stable post here, of the surge that was coming in. So this was about the time of the peak surge, and unfortunately, there's a lot of damage to these buildings on Fort Myers Beach. Now, the surge was predicted and discussed by the National Hurricane Center over 2 days before the landfall. And so it says here, life-threatening storm surge is possible, including between Fort Myers and the Tampa Bay region, potentially. And they mentioned also the other threats and impacts, like hurricane-force winds and heavy rainfall. However, as you probably saw in the media, there was a lot of discussion about this. This is the cone of uncertainty, and spoken about, unfortunately, on TV as a cone of concern, which we're all very concerned about. The cone is really about identifying the probability where the central location lies to a 2/3 chance. So basically, the center of the hurricane can fall outside the cone 1/3 of the time. That's just the way it's designed. And it's good sort of as a long-term view, but when one's thinking about the short term, one needs to realize that the hurricane is not a point, and that it's the impacts from the storm surges, wind, and the rain, and it can be many miles away, that's really what we need to be thinking about. And so we're taking a very holistic approach at the University of Miami, and this is a project that's under what's called a ULINK program that was established by our provost when he joined the university in 2017. And the whole goal of ULINK was to gather together teams of faculty in very different disciplines. And so on this list of authors here, we have a couple of us meteorologists here, but also we have environmental anthropologists, we have social scientists, we have graphic designers, we have people in human factors and education. So it's quite an interesting group of people here. And we published this paper that happened to come out at the time of Hurricane Ian, and so it's referred to quite a bit in the New York Times and the Washington Post. But this all seeded from a new initiative that was spearheaded by our provost at the University of Miami. And we'll come back to that in a little bit. A fairly grim slide here. So this is over a 50-year period. The causes of deaths in the US that are directly attributable to Atlantic tropical storms and hurricanes. And about half of the deaths come from storm surges. This was actually surprising to me when I read the paper here, was that about a quarter come from rain, and then about 11% or so come from wind systems directly. Although, of course, the wind is a big influence on the storm surge, of course. And then on top of the direct deaths, so many indirect deaths. And actually, with Hurricane Ian, in Lisa's report, that the estimated number of deaths is 156. 60 of those were from direct deaths, but the other 90 or so were indirect deaths. And so many of those included cardiovascular failure or vehicle accidents, issues with handling power or being electrocuted. And then with Hurricane Ian, there was also a very acute problem of people not being able to receive medical attention when they really needed it. And so it's really important to think about building resilience, and there's just so many challenges, as we've already seen, with Hurricane Ian being a particularly tragic example of that. So in a longer term, that it's important to think about land use policies that don't build in floodplains, for example, and then think about buildings that can withstand storm surges, wind damages, and flooding, both at the coast but also inland. The inland flooding is unfortunately a major killer here. And in the top right-hand picture here, this is an independent building organization that rates the states in terms of their building resilience. And green is good. And so Florida is in a pretty good situation with its buildings, especially South Florida. And much of that came because Florida was hit by Hurricane Andrew in 1992, and then there were 4 hurricanes that crisscrossed Florida in 2004. And especially since 2004, Florida has really adhered to pretty good building codes. Some of the older houses, of course, are still fairly vulnerable, but at least Florida, compared with many of the other states, has done fairly well in its recent buildings. And then the establishment of power grids, because of course we get, like with Hurricane Ian, 2 to 3 million people losing power, need more robust transportation. Hurricane Katrina was a big example, a very sad example of that. And also sort of the better design of roads and things like hotels being prepared to take on evacuees. Many public health impacts need to be addressed. One being the real challenges, especially to the patients on dialysis or other machines in hospitals. And then they receive a forecast that says, well, there's 20% chance that a hurricane force winds are going to reach the hospital. What does one do with that information? So a lot of very difficult decisions to be made there. Hurricanes can also cause release of toxic chemicals as well. So patient admissions to hospitals go up quite a bit, also just from respiratory issues as well. I won't talk about this very much, but of course this is very much tied into sort of thinking through many of the legal and financial elements to do with the hurricane impacts. And now we'll sort of transition a little bit to event by event and think about improving forecasting, also about, aligned with that, improved communication of impacts and uncertainty. That unfortunately all our forecasts do have uncertainty. That's just something that we have to deal with. We don't like managing uncertainty. I don't like managing uncertainty, but we just have to. And with this improved communication of improved forecasts, so that can lead to hopefully better decision-making by officials and residents, and better responses, and also better preparations for those responses, such as gasoline and other supplies. And this is emphasized a lot by Lisa and her colleagues at the National Hurricane Center, is that training and education are absolutely critical. And it's just an ongoing process. It's not going to just occur one year, but continuous training and education is really important, and outreach. So now moving to some of the challenges that are related to hurricane forecasting. So the Rosenstiel School, many faculty and many students work on various different elements of hurricanes. And so many of you are probably familiar with the sustain tank outside. Whoops, sorry, in the new building there. I wasn't supposed to do that. Okay. The sustain tank over in the new building over there, or relatively new. It's now 8 or 9 years old. And so we'll show a little work from that, and there's plenty else on the hurricanes.earth.miami.edu website about many of our activities. But I'm just going to pick a few activities that some of my research group members do here. And it's useful to think about the behavior or the life cycle of a hurricane. And so about 80% of the most intense hurricanes are formed from what are called African easterly waves here. And then there's a lot of questions as they move across about whether not just they're going to form, but are they going to intensify, and if so, by how much? And so there are all of these sort of challenges that we have with formation, structure, and intensity change. And then we're also, as I mentioned just briefly, that we're working on communication of risks and impacts as well. So I'll show a little there. But we'll start from where it all begins, which is hurricane formation or genesis. And so many of these hurricanes form from African easterly waves. And so here's an animation by my Ph.D. student, Quinton Lawton, who's in the audience. And so you can ask him about this. But it looks very disorganized, and that's because it is. So it's a messy diagram. And these waves are initially just a lot of thunderstorms that are not really organized at all. But as you'll see now, that they're starting to sort of form a little bit of rotation here. And so that's sort of the onset of the genesis process. So this was a storm that was Tropical Storm Victor, which nobody except Quinton will really remember. Well, maybe some of the rest of you will. And then also following on from that, smaller waves interact with bigger waves. So let's just look at the top diagram here. So here's Africa, here's Miami, and here are the little African easterly waves all moving across along their merry way. And then we've got these bigger waves in red and blue that are called Kelvin waves. And the blue part corresponds to where there's sort of more moisture, more clouds, and more thunderstorms with those bigger waves. And so those can support the formation of tropical cyclones that may develop into hurricanes. So this is another element of Quinton's research here. And then there are also some very unusual mechanisms for formation, such as waves merging. And we've seen very few publications about this. And so if we follow here, this is also messy, which is also part of the point. But we see we've got these two black dots that merge here. And it'll cycle, and you'll see the black dots again. And this looks very disorganized, but it actually formed into Hurricane Laura. There was a Cat 4 that made landfall in Louisiana. The forecasting of this was so difficult before it formed that it was actually predicted 5 days out to be a Cat 4 in Miami in some of the computer models. Thank goodness those models were wrong, but it definitely sort of had our antennas up a little bit that, oh goodness, this could be something, but right now it's nothing. So we really need to understand these a lot better through elements of modeling and various sort of imagery like this. Also, what's very important, as Lisa had mentioned, is flying into the field. And here's an example from a NASA field experiment that Quinton and Alexis Wilson were deployed to. And they were deployed to the Cape Verde Islands here as part of a NASA field experiment. Here's Alexis by the DC-8 aircraft here. And so the aircraft is this flying lab. And so one gets live data. There's radars, there's various other instruments that are released from the aircraft. And then those give much higher definition data than those that are available from satellites. Now, you also try and keep the models honest as well. The models are by no means perfect. They're built on a set of equations. They're getting better, but we need the observations as a reality check. And so we see here are the African easterly waves. They interact with the Saharan air layer, so there's a lot of dust here. And you see some of that dust sometimes on your cars. Sometimes around, say, sort of June or so, it makes it all the way to Miami. And here's a photo from Quinton on the plane showing the dust here right from the plane. So yeah, it's pretty sort of murky and rather strange kind of scene here. Moving on to a different topic, intensification. So there's a big question in the community about why some storms, such as Ian, intensify rapidly, whereas other storms do not intensify rapidly. And so another of my PhD students, Sam Nebelitsa, that she's working with Professor Dave Nolan and myself and Brian McNulty, who's in the audience, on a couple of these questions here. That are there these sort of sensitivities? So do small changes in the wind and the moisture make a big difference in how a hurricane may or may not intensify? And then also, very interestingly, hurricanes, of course, we know they have clouds and rain, but they also have hail and they also have snow in them. And how those are specified is very important, and not much is really understood about what's called a microphysics in the hurricanes. And then another student, a PhD student, Kerry Englert, who took this very nice movie from Hurricane Earl here, that she's very interested in the day-night cycle, or what's called a diurnal cycle of clouds, and how that might be affecting intensity change. So they're all doing very interesting PhD research here at the Rosenstiel School. And then a little work that I'm doing, that I also work in the summers, and I was on sabbatical at the European Centre for Medium-Range Weather Forecasts. That you may have heard of that as the Euro model. That there's always this game that's played a little bit between the American model and the Euro model, but they collaborate, and I collaborate with both of them. And so modeling is a very interesting question that Dean Avissar has his own global model as well. And so these models are built with many, many different grid points. There's actually, believe it or not, 10 million of these sort of little boxes that have to be solved for. You need all of the wind, the temperature, the pressure, the moisture, and all of the intricate physics that's going on to be represented in each of these 10 million grid points around the globe. And so this is what's referred to as a global model that the European Centre predicts not just hurricanes, but weather across the entire world, including the poles and Asia and so on. And so I've been working with them on an experimental version of the model, which can now resolve eye walls in hurricanes, whereas the current operational versions that you see, that they can predict the track fairly well, the path of the hurricane, but they don't necessarily predict the structure all that well. But one needs to get the eye wall right and the rainfall right to really be able to better predict the hazards here. Okay, we'll shift gears, but stay in research into satellites. And interestingly enough, and this is a total coincidence, there's a Cygnus workshop that's been taking place in this auditorium today through to Thursday. And so the seats that you're filling here were filled with scientists who are working on this constellation of satellites, and also a new constellation of satellites called Tropics. You probably recognize two of the people in this picture, and the third is also in the room, Brian McNulty here. And essentially with Cygnus, there are 8 satellite receivers that essentially measure reflected GPS signals. It's a GPS that our phones all use. And then you get these stripes that then retrieve the wind speed. Now, what's really interesting with Cygnus was that it was designed initially for hurricanes, but some of its main successes have actually been for measurements of soil moisture or flood inundation. So this is one of the great surprises that we have much of the time with science, is that we're trying to test a scientific hypothesis or an instrument for something, and then it ends up being useful, especially with something else. It's a total surprise, even to the designers. So that's a really nice story. And then finally on the research side, we know that the cone is confusing. That's old news that scientists at the Rosenstiel School have published on that even 15 plus years ago, Kenny Broad and others. And so we really need to think about the hazards and the impacts here. And also we need to think about how to include elements of uncertainty, different hazards at the same time, like with Hurricane Ian, that it's not like one hazard happened and then another happened. They're simultaneous. How long they occur as well, so the whole duration, not just the onset, and how to make graphics accessible. So we're just starting to work with the National Hurricane Center and the National Weather Service on a new NOAA grant on graphical risk communication. This is just a very early prototype that's really very much borrowed from the National Weather Service's hurricane threats and impacts graphics. That these graphics are out there, but they're sometimes hard to find. But we're really trying to build in all of these considerations and then take those out to the public and have public surveys, focus groups, also bring in underserved elements of the population as well. So it's really reaching to broader communities, that it's not just a bunch of grad students or people who are already quite educated who are looking at this. Okay, so now I'm going to totally switch gears and put my administrative hat on here and talk about the Climate Resilience Academy. And so here's the website right here, a fairly intuitive name here. And so just a little bit of a background about the Academy. That this was really a brainchild of President Frank at the University of Miami. So in his inauguration speech, he mentioned that, well, Miami as a city needs to be more resilient to aspects such as sea level rise. And also the university needs to play a role as the University of Miami to really build this expertise and to work with stakeholders and communities to try and tackle these very hard problems. And so he hired the provost in 2017, and or through Dean Avisar, that I got to know the provost fairly well. Then provost caught me in a very weak moment in the middle of a pandemic in 2020 and said, "Oh, you're doing this." And it wasn't really like, oh, yes, they weren't even really begging. They were just like, here, you're doing it. And I was sitting on a couch in Reading, UK, and they knew that I was pretty trapped during the lockdowns. So I ended up working with Rudy El Khoury, who's a dean of architecture. We didn't know each other, and we had a zillion Zooms, and have had a great time working on this. That I tend to sort of be this windshield wiper between administration and research, and so I've actually relinquished this from January to get back into research, but I'm still sort of working quite a lot, just not day to day, on helping build the academy, which I'm very excited to talk about. So as we know, even from today, that Florida gets flooded. There are multiple other threats as well that we read a lot about, rising sea levels sort of over the coming decades. Also extreme heat as well. And I think that Brian has mentioned that on Twitter that we've had like a record number of days already this year, so compared with other Aprils, well, up January through to April, where it's been at least 85 Fahrenheit. So, yeah, we're certainly sort of hitting some extreme heat issues as well as flooding and the rest of it. And so these problems are so big that individuals can't really solve them by themselves or with one or two grad students. So it really needs big communities to come together. And an example of this is our local governments here at in Miami-Dade County and the beaches. And so they've designed this Resilient 305 plan that's very intricate, very detailed, and gives this roadmap for a lot of different elements of resilience, very much so on sort of the society side. And so we'll talk quite a bit about some of the examples of that. But first up, Dean El-Khoury and I put together a fairly long and convoluted looking mission statement, but there's a lot underneath each of these words. That first of all, it's very interdisciplinary, that we can't just do it in one school, that scientists at Rosenstiel sort of work with engineers and architects and public health scientists. The research and education here is very much driven by problems, more so than just sort of driven by an idea or a textbook. And so, of course, as a university, we want to build the training of current and future generations, many of whom are very interested and concerned about these resilience issues, to really deliver solutions here and really build partnerships with all different sectors. So thematically, we put this together to really cover the expertise across the university and to identify and build capacity. So the top left-hand corner here is infrastructure and environments. That's a bit more the human and the built environment, like the engineering elements, the architecture elements, the biological elements, coral reefs, and so on. On the top right-hand corner, we've already spoken a bit in the context of hurricanes about the human health side. The societal health is, of course, critical. Elements, say, of migration, that as our islands, I live in an island too, that as we get more and more underwater over coming decades, people are going to be migrating inland. And what's that going to do to society? And how can Miami stay as a prosperous city with this sort of creep of the sea levels? There's a very interesting book by Jeff Goodell called The Water Will Come. As some of you may have seen it. It's a very good read. And he came and spoke at UM a couple of months ago. And then connected with all of this is economic development, of course. We need to sort of continue our thriving economy here, but be aware of the potential stresses that we're facing and factor those in. So just sort of the map of the university really here, that we all know where we are, but then we also collaborate a lot with the medical campus. And then also, here are all of the all the schools with academic programs on the main campus. And so we've worked, and it's just been fantastic, with all of the deans and many of the faculty. We have about 250 faculty across the university on our academy mailing list, and they come from all these schools. Of course, some of them, like engineering, sort of play a larger role, but even like we hung out with a faculty member of music, and that's really awesome. He's a jazz musician who's just sort of, he really communicates a climate theme quite a lot at his concerts. So yeah, wherever you look, there's always like some people with a very unique angle and area of expertise that are connected to this very challenging problem. So with the Academy, it was launched just a year ago on Earth Day, quite appropriately. And it was made possible by Eric Levin, who's a local businessman here in Miami, that he wanted to be here, but he had to go to something else that he had also donated to as well. But yeah, he's here in spirit for sure, and he's a middle person in this photo here. And so now we're recruiting a full-time executive director, and so we've interviewed 2 candidates so far. So we're just right in the process of this. And then that person will really be the hard charger with us supporting them on building the Academy and taking it to the next level. There are many people here, many of our administrators, but I wanted to really point out the person here who's on Eric's right shoulder here, and that's Jane Gilbert. She works at Miami-Dade County. She's the first chief heat officer in the world. So it's quite forward-thinking of our mayor, Daniela Levine-Carver, to appoint a chief heat officer. And now there are cities who are following Miami. And so Phoenix has one, Los Angeles has one, Athens has one, and there's probably a few others who have established a chief heat officer as well. And then a lot of the Academy's activities so far in its sort of fledgling state. We'll talk a little bit about the education element. I'll show a video of the undergraduate course. And then we've been convening symposia as well, and then deans have been working on hiring faculty as well. So it's very much a supporting entity here. It's not a new college, it's not a new school, but it's really here to support all of the schools, this one and all of the other 11 schools as well, and really bring in many of the external stakeholders. So here are just some photos just from last year's symposium, and then also a big tech and business expo on Miami Beach that we were featured there too. The next one is just in 9 days' time on Miami Beach, so look out for that. And then we just had a couple of symposia in the last couple of weeks. We had Smart Cities, and here's our mayor who was there, and she was also at last Friday's Climate and Health Symposium as well. So now on to the educational aspect, that I'm going to take a little bit of a break from speaking myself and just play a video in which our provost very eloquently introduces this new undergraduate course that was developed by our Academy's Committee on Education. So I'll just put this in full screen, and I will hit play.
We are bringing together 13 of our top faculty members from various University of Miami schools and departments in a highly innovative and interdisciplinary course that would take our students on a problem-driven and discussion-based journey, reflecting on climate change and how human activities contribute to it, extreme weather events, building resilience in structures and networks in coastal cities, climate-driven migration, climate justice, climate equity, and gentrification, as well as climate laws and policies. Along the way, students would also get introduced to the fundamentals of data collection, data modeling, geographic information systems, otherwise known as GIS, and data visualization, which allowed them to iteratively and actively experiment with how to solve a real-world problem that would collectively culminate in a capstone project. The lectures of our faculty members are recorded cinematically in various field locations in South Florida, where they demonstrate and share the visual evidence of their research topics in a flip format methodology. Facilitating students' reflection on these immersive experiences, the in-person classroom discussions and uniquely designed critical thinking workflows are essential to help students develop a sense of personal responsibility and political agency to navigate the world with conviction and creativity.
Okay, there we are. And we see there's a lot of different course codes here, and this really exemplifies the point that the course is really open to students from all different disciplines and interests. So the humanities, the sciences, engineering, you name it, that this course is really for everyone. And so it's in its second semester right now. We're hoping to grow the course further and then build some spin-off courses that may be more specialized at the undergraduate level. Then at the graduate level, there are multiple programs that are already established before the Academy was established. And here are just an example of 4 of them that either sort of solely or jointly run by the Rosenstiel School. The acronyms here, or the abbreviations, MPS stands for Master of Professional Science. And so that program, and there are many different tracks, I've only listed one here. The professional masters, as the name suggests, is for students who have an interest in going into the profession. And so they're not necessarily interested in research or writing peer-reviewed papers, but they're very interested in getting one foot in the door in the profession. And so that's been a super successful program, will continue to grow at the Rosenstiel School. And here's a particularly relevant track in climate and society. Then there are also other programs that around the university as well. And we're working with all the directors of each of those programs so that programs better connect and students get experiences in the other programs and really cross-pollinate and build a community. And so one role of the Academy may be in synergizing some of the internships that the students are looking for as well. And then just wrapping up now, so just some snapshots of some of the projects at the university. So a very high profile one is building coastal resilience and protecting our coastlines. This could be done through deploying or developing hybrid reefs that are partly artificial, partly natural. And so this just received a very large Department of Defense grant quite recently. A second one is an online mapping tool to inform planners and policymakers of what some of the rental costs might be and what some of the challenges they may be facing as people are migrating more. Interestingly, this is sponsored by JP Morgan and Chase. An engineering project on building more resilient structures is here, and so, of course, we need these to last through hurricanes and the rising sea levels. Building economic resilience, of course, and evaluating economic resilience is very critical, such as the impact of building resilience infrastructure on the property values. And then also the response of the insurance industry to active hurricane seasons in Florida. So we have faculty in our business school and Rosenstiel and other schools who are working on this type of problem. And finally, this is a brand new project, which is spearheaded by David McMillan, a new faculty member in the medical campus. And that's designing focused and inclusive programs for climate adaptations for patients who with a spinal cord injury and disorders. So that's 5 out of at least 87 projects at the university. And so as the Academy that we're looking to, especially once a new director is hired, to really build this out and sort of think big in how we can sort of serve the community in addressing these very difficult challenges. So with that, I think I am done. So thank you.
Thanks, Sharan. Excellent job. Really appreciate your many years of service for the university, as well as your leadership at the university over the past few years. And it is now my pleasure to introduce Jennifer Dillon.
Thank you so much for everybody who came out here tonight. And I just wanted to say thank you. Thank you, Sharan. Thank you, Lisa. Thank you, Ronnie, and all the scientists who are here in the audience tonight who do this kind of work for us. I'm so glad that it's not me trying to do all that modeling, but thank you. And I just want to say really quickly before we do our questions, because we're going to take some questions from online and we're going to do some that are in the audience here, but I wanted to say, if you would like to help us help students come to this fine school to do this kind of research with experts like Sharan, please see me. My information is right here. I'd love to speak to you about it, and thank you so much. We'll go ahead and move on to our questions, because you've got a lot. So come on. I have lots of them online, so I'm sure we'll have lots of them in here too. Where do you want to start?
Okay, yeah, shall we start with one in the room? Okay, I guess the dean gets the prerogative here.
You indicated that about a quarter of the fatalities were coming from rain, and I'm trying to figure out what exactly that means. Is it the flood that is generated inland by rain, or what's the? How do you explain?
Yeah. So the question for those who didn't hear and those online was that we showed that 27% of the fatalities came from rain, which seems, it surprised me certainly when I saw that statistic. Interestingly, inland flooding is a very major issue that in Ian, I forget, Lisa might know the number, but there are a few dozen people, I think, who perished just in inland flooding. I saw this a little bit myself when I evacuated to Houston when we were evacuating from Hurricane Irma, but Hurricane Harvey had just hit Houston. And there's just, what one could just see when you have just feet of water that are sort of piling up. And it does surprise me a bit that there is sort of that level of fatalities, but yeah, sort of moving objects and people being out. Electrocution is a big issue. I don't know whether that's attributed as a direct or indirect death.
It comes from the flooding due to the rain.
But it's the flooding due to the rain. It isn't the direct impact from the rain. Yeah, sorry, I didn't clarify that. Okay, we'll take a question online.
Yes.
Oh my, some of these are essays.
A lot of them. As well as interdisciplinary efforts at UM, have you reached out to the additional Florida institutions and or others on the East Coast? Has any other university approached climate resiliency in this way, or is UM a trailblazer in this effort?
Yeah, that's a really good question. So we can't go it alone. And of course, thinking about South Florida, that Miami-Dade County says, well, it's really important to have everybody involved here and sort of really capitalize on the talents everywhere, that it's not one university against another. And so one example of that is the Resilient 305 collaborative that Professor Amy Clement here is very engaged in. And she works very closely with her counterpart at FIU, for example, and also Miami-Dade College. And so there are also sort of many meetings through Miami-Dade County and the beaches where multiple institutions are involved. So it's really a community effort, and that's what we all want to build. As to the second part of the question, that there are, we're not alone in sort of trying to do this. I think we have a fairly unique approach with Building Academy, that we're really trying to serve and not really compete. But there are also other schools or universities that are building schools of climate. But then there are challenges with those as well. So we're trying to build a new school just organizationally and how to build new programs. But here we're very much a supporting entity, so we may be a bit different administratively.
Somebody have it right here?
It seems like in the last several years, even a decade, that hurricanes now seem to be coming more west coast. Some people will refer to as like this Hurricane Allen now being the Gulf of Mexico, and not so much coming to us from Africa directly across. Is that being steered in part by the Saharan dust issue, or are they unrelated, or is this just something that's really not a trend, but people think it's a trend?
Yeah, that's a very interesting question, and definitely that's almost a title for a research paper right there, because I'm not sure that there's a very clear answer to that. And so the question was that does it seem as though there are more hurricanes that are veering towards the west coast of Florida. It's really quite hard to address that. It's very, very interesting, but I'll probably be a bit speculative about it. We have had more storms that rapidly intensify in the last 20 years or so compared with, say, the previous 20 years. And once they sort of build their intensity, that many of them do end up going more westwards towards the Gulf of Mexico. So there's also like Katrina, Ida, Wilma, many of those storms. So there are a lot of Gulf landfalls as well. And then, of course, Florida is kind of in the crosshairs there too. I think that with Western Florida, it's a little bit too fine-grained to give a very definitive answer to that. But perhaps just through more storms, that we need to do research on this, that are building enough intensity that they sort of reach the Gulf of Mexico, that might just be a consequence there, and that's why there've been some of those high-profile landfalls.
And the Saharan dust, how does that factor in?
The dust is generally hypothesized to be an adverse factor, that hurricanes or tropical storms generally struggle to form when there's dust there, because there's also relatively dry air as well. But that's also a bit of an open question. There have been storms that have ingested a bit of Saharan dust and have still maintained themselves. But they may have maintained themselves in spite of the dust. So the dust is not necessarily an influence in the steering of the hurricane, but it does have an influence potentially on the intensity of the hurricane. But the consensus is that it generally is not acting to strengthen it most of the time.
I'm going to toss you a softball this time, one you can easily answer. How many students were in the first semester, and how many do you plan for the next?
All right. Oh, thank you. Yeah, that might be a tough one. I would have known those numbers off the top of my head when I was associate dean. So in this last year's admissions, so that's 2022, fall 2022, at undergraduate level, how many have we had admitted?
I think that she's asking regarding the class, the resilience class.
Oh, sorry. So, yeah, for that course. Yeah, my apologies. For that course, there's been about 35 undergraduates in each of the 2 semesters. And you saw them all sort of crammed into that room there. And so now we want to take it to the next level and expand it. But we also need the resources, and we'll need to sort of fill out the classrooms. We're doing it as a pilot test, but now I think it's building maturity and we'll be ready to develop further. Great question, thank you.
I'm going to take one from online. Someone is asking, how can we stay abreast of the Resilience Academy activities and research remotely?
Okay, great. So the main place to go is the website, resilience.miami.edu, which Brian maintains. And so, for example, the latest developments over the last 2 weeks were 2 symposia. So there was one on smart cities and there was one on climate and health. And so all of the talks are linked there in the posters. So there's information really through that website. And then as the Academy grows, that it will continue, or it will build newsletters. So right now we just have an internal mailing list. But then we will want to reach out through LinkedIn or other fora to have real widespread communication.
Super. Somebody have another question from the audience? Up here.
Something I've always wondered, why do weather patterns across the United States come from the west to the east and hurricanes come from the east to the west?
Oh, that's a fantastic question. That sounds like a comprehensive exam question there. Probably. So it's generally through the rotation of the Earth. That's the first element. And then another element is that the sun heats the Earth as well. And then it's irregular, or the heating's not uniform across the whole Earth. And so the combination of those 2 things then causes the formation of the jet stream at the high latitudes, which is this sort of ribbon of air that is about sort of 15 kilometers aloft, and that flows west to east in both the northern and the southern hemisphere. And so that's the first part of the question right there. On the other side, the African easterly waves, as you pointed out, that they move from east to west. And that's also due to a difference in the temperature. But what's called a temperature gradient is reversed in the tropics. And that's largely just through how Africa is set up, just with the desert and with the forest there. That then creates this sort of change in temperature across Africa. And what that does, it creates its own little jet that's called the African easterly jet. And then the waves form as little instabilities on that African easterly jet. So I hope I got that right, Quentin.
Thank you, Sharan. That was wonderful. I think we've run out. We're at the end of our time. So I just wanted to say thank you very much. If you have questions, I'm sure Sharan would be happy to email. You can email him, you can email me, and I can pass them on to the expert. So I wanted to say our next lecture will be coming on April 24th, featuring Dr. Mandy Holford. And if you would like to see this webinar, it has been being recorded and will be up on our YouTube channel in the coming days. Thank you very much and have a good evening.
Thank you all.